Good evening, everybody. So thank you for being with me for the last talk of the session. So I'm going to give you an update of what we did at UQuark. The Shibugomo transect, this work is almost completed. There's just a few more papers to write, but I'm mostly going to talk about the thematic project today. So to start, I would like to thank the great team of students and collaborators and industry partners we had for all of these projects. So the team is growing and growing, so it's really fun. So today I would like to talk about first the Shibugomo transect, very quickly, as I said, and then I'm going to talk about thematic project 1 through 3. So for the Shibugomo transect, as I was saying, it's done for the most part. Most of the master and the postdoc project are completed by now. We had one last PhD project on the Shibugomo pluton that was Alexandre Crépin. Due to lockdown, it was turned into a master project, and I'm going to give you an update on this in one moment. Regarding publication, which are still to come, there is something that was done by Marie Kiefer in collaboration with Laval University on the isotope around the molybdenum and the late structurally controlled mineralization in the ozone complex. So this is which will be submitted soon. And then there is paper to come by Pierre Bedeau on the detrital zircon and the sedimentary packages. This is a very important topic for the Shibugomo area. The sedimentary basins are quite thick. We don't know why. So this will bring more constraint on these basins. One paper to come on the Shibugomo pluton and its copper gold porphyry style of mineralization. And then the age compilations that that's a project it's a collaboration between me and Mike Hamilton. We've got the first result. We are looking at the maps and the compilation. It's really exciting as well. So this is just an overview of the paper which have been published so far, either as part of the Meteoros project or as a leverage project, which are linked, which wouldn't have existed without the Meteoros project anyways. That's why I've got everything in here since the beginning, since 2019 for the oldest publication year. So regarding the Shibugomo pluton, that's Alexandre Crépin with a student working on this. It's a collaboration with Dan Contac. What we knew from the Shibugomo pluton is that it's been intensely studied in the 80s. So we knew it's dominated by tonalite in orange and diorite in blue on this map. It's a TTD suite. It's not your usual TTG suite. We know it's associated with a copper gold porphyry style of mineralization, which has been referred to, the mineralization that has been known to be a porphyry style of deposit since the 80s. There is very clear characteristics like dikes that cut and are cut by the mineralization. These dikes have the age and the chemistry of the Shibugomo pluton, and there's plenty of other characteristics. This is a porphyry system. So even looking at other things like alteration or pyrochemistry, it's pretty clear that this is a magmatic hydrothermal system. So what Alexandre did was to revisit a few outcrops that are still easily accessible. There was no point running all over the pluton because Denis Rossico already did that in the 80s. So the point was to go back to a few of these selected outcrops, get thin section, do additional mineral chemistry, and especially look at zircon. And these are preliminary results on zircon geochronology, and we it's quite amazing the amount of data it added to what we had. Previously, we thought that the Shibugomo pluton was built in two main phases, one during the thin volcanic stage, one during the thin tectonic stage. That remains, that's true. But what is new is that the construction phase during the thin volcanic stage is much longer. It's not 1 or 2 pulses a few million years apart. It's really a long duration. It's a long, a lasting magmatic event. So it's really interesting. It questions how this pluton assembled and how things build up until it was able to produce a copper gold porphyry style of mineralization. Alexandre also did a compilation of mineralizing styles, and that's the main result is that we can talk more about the dynamic of how did the fluid circulated in this rock. It was mostly structurally controlled, but what kind of structure? Breccia are restricted to certain areas, so this would be an interesting discussion as well. And we also have data on fluid inclusion. This was done by Dan Contact because travel was challenging. And the results show that these are high salinity fluids that form this fluid inclusion. These assemblages there's really one assemblage of fluid inclusions. So it's pretty clear this is a magmatic low thermal system. So porphyry style of mineralization is something that is going to remain for the Shibugong Pluton, and we are going to bring more details on the mineralizing style and on the way the Pluton assembled. A side project I'm carrying in collaboration with Dore Copper, the company that is exploring in the Central Camp area at the moment. It's also done in collaboration with Danny Sava on the lab mater at UQuac, is to look in more detail into the chemistry of pyrite. We've received a few samples from the mineralized area, which was drilled recently. And this is the kind of map you can do on the new laser ablation instrument at UQuac. You see the size. It's a pretty big map. It was done pretty quickly with the Femto new instrument. It's quite amazing. So we are carrying statistics at the moment on this, and hoping to connect this with what I've already done on pyrite chemistry in the Shibugong area. Okay, moving on to the thematic project. The first thematic project was carried on syntectonic magmatism. The question we had was, what is this magmatism? What is its chemistry? What are the state of the classification we have? Because we know it's a very heterogeneous magmatism that occurred during the syntectonic stage. We know some of these intrusions are associated with intrusion-related gold system. Most aren't. They are sterile systems. So we wanted to figure out what type of magma are we looking at here, how heterogeneous is it, and do we need to review the classifications that we are using? So just to give you an overview, we know from Moyen 2019, for example, that we have alkaline intrusions at the onset of alkaline magmatism for the ABTB and other greenstone belt. We've got sanukatoids, potassium-rich TTG suites, biotite granites, and that's and possibly other things. So the initial plan was to compare this magmatism in the Wabigoon and ABTB greenstone belt. It turned out Patrick had initiated a PhD. It had to be turned into a master. And this is the main result from this master so far. We ended up comparing 3 intrusions, 1 from Wabigoon, 2 from the ABTB sub-province. These 3 intrusions, they are sterile. They are not associated with any known mineralization. So looking at their pathology, looking at their overall chemistry, and looking also at the chemistry of amphibole, hapatite, and zircon, and titanite as well, we were able to come up with an explanation for the lack of mineralization in this area. So before I move on to this, there is some pretty meteorological textual relationship here. You've got hapatite and magnetite and zircon all in the same cluster. These are phases that crystallize very late in the residual melt, and you can see that this zircon got partly destroyed in this sample. And coming to the explanation, it's summarized in this paper, which has been submitted recently, is that these magmas, they seem to be lacking a significant amount of sulfur. The rest is okay. They have the right chemistry. They are enriched in incompatible element. The oxygen fugacity is high, which is important to carrying gold in these magmatic systems, but the amount of sulfur is not sufficient. And in order to dissolve gold in a magma, you need sulfur, otherwise it doesn't work. And you need the right oxygen fugacity, but you also need sulfur in the system. So it seems to be what is lacking in this system. So it's interesting to look at this unmineralized system, because we can look for what could be missing. And the main answer, again, from this project is that the amount of volatile seems to be, there's enough water, there's CO2, there's all of whatever you want, but sulfur is missing. So that's the explanation we've got. That's what came out of this project. Okay, moving on. Thematic project number 2 was on alkaline magmatism and sanukatoid. The Sanukatoid project, it was to be carried with the help of postdoc, but immigration never came through. So it ended up being moved to another of my PhD students. I'm going to talk about that in a moment. The first project is a master project by Taylor Washwita, looking at one of these alkaline magmatic system, which is mineralized. This is the example that was selected is the Dwe project, which is being explored by Maple Gold, and it's now they are joined with Agnico Eagle. So this system is really interesting. It has the typical characteristics of this, what we call intrusion-related gold system, and we are never sure if the orogenic gold system actually played an important role in this kind of area. So it's typically your cyanide-associated mineralization disseminated with high temperature alteration like potassic and sodic metasomatism. But at the same time, you've got a part of the mineralization which is structurally controlled. So it's always hard to figure out which of the system between the intrusion-related gold system and the orogenic gold system actually brought the gold to the upper crust. It could be both. It could be just one mobilize the other. It's always the question. So we address this question using the example of Dwe. So you see the rock types. There's a heterogeneity of texture and alteration styles. Just the red and white rocks, it's different alterations. So Taylor has been documenting all this. Before I move on, I forgot to say that this is a collaboration with Roche Sherlock, Benoît Dubé, Fred Spidol, as well as probably Olivier Cote-Manta now. And these are a few more additional results that Taylor produced. She looked at mineral chemistry. It's always a challenge in cyanide because you don't have many minerals to work with. The zircon can be completely destroyed. I'm going to talk about that in one moment. You have the carbonate, you have the feldspar, and you have the sulfur that you can play with. So Taylor has been doing all of this. The pyrite chemistry data are they have been acquired. They will be processed soon. For the rest, you see that the carbonates are mostly in the dolomite ankerite solid solution. This is the alteration, the carbonatization we see in every rocks. And you also have carbonatite injections. They are mostly made of calcite. So we have a clear distinction between these two things, carbonatization and carbonatite injections. So we are getting a clearer and clearer picture of this alkaline carbonatite intrusive complex. Just would like to say to finish that this carbonatite-bearing alkaline complex, they are restricted to the northern part of the Abitibi greenstone belt. We still don't know why, but it's the observation. Now, to complete this project, we took a few samples for zircon separate last year. This was to be processed by the postdoc. As this couldn't be done, I did the processing myself. So there is data coming on zircon chemistry, and for the Dwe cyanide, what I can say on this, that one of the samples had the most uranium-rich zircon we've ever seen, so the zircon was destroyed, but the other sample will give us insight into alteration and processes and physicochemical parameters for the Dwe cyanide. Okay, so the project, also part of thematic project number 2, was to work on Sanukatoid magmatism. Sanukatoid are a very enigmatic type of magmatism. They've been viewed as a missing link between TTG, tonalite-dominated magmatism, and syntectonic potassium-rich magmatism. Now, there is still this model out there, and it doesn't exactly fit with the age of all the intrusion we can refer to as Sanukatoid. So we are still thinking about, are they really a missing link, or are they just a peculiar type of magmatism? So this is a PhD project that was initiated as part of my NSERC funding. It was a collaboration with Michel Gebrac, and Esther is a PhD student working on this. As we had to reorganize thematic project number 2, we brought Esther into the team, into the Metallers team, so that we could reach all target on this Sanukatoid thematic project. So Esther started recently, she started a year ago. She completed her courses, and she's in good way to complete her first paper, which will be on the Opemiska and Barlow pluton in the Chibougamau area. These two plutons are it's quite a large volume of magma for the syntectonic period, and they have been referred to as Sanukatoids for a long time. So Esther has been looking at their chemistry in detail these past few months, and it turns out that they have chemical characteristics of Sanukatoid magmas, and let's say they don't fully fit into the current classification. So this is something we need to think about. And there is also a lot of work done on amphibole, hepatite, and zircon chemistry. This is being processed at the moment. This paper is being written, so there will be a publication soon. What I can say to conclude is that it's very hard to classify Sanukatoids when you are missing the most mafic phase of your pluton. This we knew, so that's why we need to extend this project to other examples of Sanukatoids. What I can say also on this project is that Esther will probably pick up from where Patrick left off, because we still have a lot of a big compilation on syntectonic magmatism, including Sanukatoids. So Esther will help us think about this classification, see what we can do. Do we keep what we have, or do we produce a new one? And hopefully we will be able to get out of the Abitibi Greenstone Belt with this project to think about what Sanukatoids are in Greenstone Belt around the world. This also is a compilation that Esther has already started. Before I move on to thematic project number 3, just want to say that there is additional paper which have been published or which have been submitted, which are related to what we do in my research group regarding synvolcanic and syntectonic magmatism. So this includes the papers on differentiation processes in TTG suite, and also compilation on heterogenic model as well. So all of this is published. And I just want to signal that last year we participated to the GSA special issue. So these are 2 of the papers accepted recently. I'm pretty sure there is more. So this was a good opportunity also to advertise the work done as part of the Meteoros project. These are very short paper, and GSA is a high impact journal. So once this special issue comes out, I'm pretty sure it will be a good publicity for the Meteoros project. And the last thematic project, it was initiated last January with one PhD student, Theo Hassan Ali. And the aim of this project was to work on the crustal dynamics, looking at one of the big TTG intrusive suite to figure out how this intrusion assemble in the crust and how do they differentiate. And depending on the way they differentiate, it can tell you whether you had compressive phases or extensional phases, that kind of thing. So that's the aim of this project. So we selected the Kenogami-C complex because it has been already worked. There's already a lot of mapping which has been done in this area by the Ontario Geological Survey and by Ben Moyen collaborators and others. So we have something to start with. It's easy to access. So far what we have is a few samples I collected last summer. So Theo has already started working on this samples. The first step will be to look to perform zircon separate to see what we can say about zircon ages, but mostly on their trace element concentration. And next year there will be a bigger field work to take as many samples as we can and to do what we did already on the shibuya pluton, is to look at trace element, but also to look at ages. Because having more geochronological data using laser ablation, it's quite amazing the definition, the resolution you can get, and you get insight into the dynamic of these systems. And what I expect is also to see what we saw as a shibuya pluton. It's a long process of assemblies, not just 1 or 2 phases, but several injections successively emplacing through time to form these batholiths. And with modeling, we're also going to work on fractionation again to see at what time was the magma injected frequently, and at what time was the process locked, and at what time the differentiation had more time to proceed. So this will give us insight on what happened in the crust in this area. A bit in the way it's done nowadays in an active subduction zone, when you can look at a flare in eruption or magmatism to see whether the shortening and the relaxing times to see this kind of dynamics in the crust. That's how we're going to approach this problem. So to conclude, I gave you just an overview of what we've been doing at the moment. To wrap it up, there's been review thinking about what metallogenic model in greenstone belt, especially on anything that has to do with magmatic hydrothermal system between porphyries, intrusion-related growth system, etc. So in each of the project, we link it to that kind of metallogenic processes. We know of work on pyrochemistry, also on alteration, alkaline intrusion, and other type of syntectonic magmatism. And we also work on tonalite-dominated intrusions, whether they are TTG intrusive suite or TTD suite. So we are gaining a large overview of synvolcanic to syntectonic, intermediate to felsic magmatism. So we are looking at that kind of magmatism through time, and we are also measuring more and more physical-chemical parameters to figure out how much gold this magmatic system were actually able to carry through the crust. Plus, we are looking at the mineralized system. So all of this gives us an overview of the distribution, the cycle of gold and base metal through the crust. So that's it for me for today. Many thanks for your attention. And well, if you have any questions, thank you.